All right, now let's start working our way towards some little bit more calculus here. Okay, so here's example 5. We want to consider the general linear function, because you know we're going to start off with linear because it's so much easier to look at, and then we can build from that. Okay, of y equals mx plus b, where we know our slope cannot equal 0, right? So we're not looking at that. And b are constants. So m and b are constants, and m can't equal 0. That's what this is saying. Okay, so here is part A. We want to write the inverse of f. Write the inverse of f in the form y is equal to f inverse of x. And I'm given y is equal to mx plus b. So remember, the very first thing we always want to do if we're going to write an inverse is to swap out those x's and y's. Let's change up our color so we can see. So x is equal to my plus b. Then we solve for that y. So I'm going to subtract my b, divide everything by my m, and I have 1 over mx minus b over m equals y. And then I can rewrite this as f inverse of x is equal to 1 over mx minus b over m. All right, there's my inverse. And that's part A. Remember, b and m are constants where m cannot equal 0. And now that m is in the denominator, that makes sense, right? M can't equal 0 because I can't have that 0 in the denominator. All right, very good. Let's check out this next part that we're going to have. I want to find the derivative of the inverse. Find the derivative of the inverse. All right, talk to me about that. I know this is not something that we typically look at, right? Because I have this and this. These two parts, the b's and the m's, these are numbers. These are constants. Think about that. Okay, so if I want to take a derivative of a constant, that goes to 0. The derivative of this part is just going to be my coefficient. So the derivative of f inverse here is going to be 1 over m. Right? So just generically, because remember, that's what they represent. So you just have to keep in mind, anytime I work in full variables, what those variables represent, and then we can go with that. Okay, now let's expand upon that a little bit here. Oh, I'm out of room. Let's expand upon that on the next page a little bit. Here is theorem 7.3. The derivative of the inverse function. Okay, and here's what it says. We're going to get mathy on it again. We're going to let f be differentiable and have an inverse, on an interval I if x naught, so x sub 0, is a point of I at which f prime of x naught does not equal 0, then f inverse is, I'm going to go to the next line, differentiable at y naught equals f of x naught, and f inverse prime of y naught is equal to 1 over f prime of x naught, where y naught is equal to f of x naught. Woo! Remember, pause it, write it down, and now here's the explanation. So f is differentiable and has an inverse on this interval. So I'm taking care of all the basic criteria right now. I don't have to worry about, do I need to restrict this, blah, blah, blah. That's already taken care of. If you have to have a restricted domain, that's set up for you in advance. You don't have to worry about that. That's what that first line means. Now, I'm saying if I have this x coordinate, all right, it's a point on there where my derivative does not equal 0. So my derivative at this point cannot be a maximum or a minimum. Ah, right, there's the light bulb. So my derivative at this point cannot happen at a maximum or minimum. Because remember, then we'll start talking about, that's where the switchover happens to make it 1-to-1. Then my inverse is differentiable at, this is just a coordinate point. F of x equals y. This is the coordinate point of x, y. It's just written in terms of function notation. And it's written in terms of function notation because this, ladies and gentlemen, is what you need to know. This is the derivative of an inverse. I'd like to point something out to you. When you have the derivative of the inverse, notice you never have to find the inverse function. Right? Look at what's happening here. To get the derivative of an inverse, this is f, taking the derivative of my actual function. I plug in the x coordinate on the derivative of my actual function, and it is just the reciprocal. That is how you get that value. That's it. Super easy, right? We did all that background work in terms of inverse functions to come up with this. And the reason why we did all the background information is because you need to know the x and the y swap. Also, if I want to look at something generic like this, look at what just happened here. If I were to take the derivative of this, my original function, what would that be? M, right? That's a constant. My derivative of this would be m. What is my derivative of the inverse? The reciprocal of it. Right? So this one is just an easy example to look at the linear, which is why we did that. Now let's look at an example that is not so easy to find the inverse of, which is why we don't have to for these. Let me go purple on it. Here's example 6. I have f of x is equal to the square root of x plus x squared plus 1. And I know that this is 1-to-1 for x is greater than or is equal to 0. Here's what I'm charged with. Find the slope of the curve at, I need to read a little bit better. Y equals f inverse of x at the point 3, 1. Now here's some things that you need to pay attention to. I am told that this is my original function, f of x. I want to find the slope of my inverse function at this particular point. What this problem is saying here, which is where people struggle with this one, this is on the inverse. So that point is on my inverse function. My derivative up here doesn't deal in terms of an inverse function, and lordy bagordy, don't you dare try to change this over to an inverse. Swapping out those x's and y's, that's called a nightmare, ladies and gentlemen. However, if I wanted to look at, oh, let's go blue. Here, what is my coordinate point on my actual f function? Yes, because you swap the x's and y's, right? So when you swap those x's and y's, then I know that that's the point on my actual inverse function. So I'm going to take this guy right here, and I'm going to find its derivative. I'm going to change this to x to the 1/2 just because that's easier to find a derivative of. So there's my function. The derivative of my function will be 1/2 x to the negative 1/2 plus a 2x. Now I want to find at x. It's super important that we did all of that background knowledge so you know you flop on the inverse, the x's and y's. So whenever I'm plugging this into my derivative is my actual f prime. The actual function derivative has nothing to do with finding an inverse function at all. Because most of the time you're not going to be able to because they're going to be freaky deaky. So this is f prime of 1 will be 1/2 times 1 to the negative 1/2 plus 2 times 1. I'm going to scoot this up just a little bit. I was hoping to still see that. F prime of 1 here is going to be, that's just 1, right? 1 times 1/2 is 1/2 plus 2 will give me a 5/2. So 1/2 plus 2 gives me that 5/2 here. And I'm going to make this happen. This is what goes into that denominator. So this, if I'm looking for f inverse prime, the derivative will be 1 over that 5/2, which we know to be 2/5. So my slope here, because that's what it's asking for, it's asking me for that slope. That slope is 2/5. Nice, right? So when you go to find the derivative, it's no big deal at all. Keep it in, you don't have to find an inverse, right? All the concept associated with finding that inverse is helpful, but for our intents and purposes, this is what you have to know. And I will never, ever, ever give you formulas. You have to know them. Write this down. Make your cheat sheet somewhere. If you want to find the derivative of an inverse at a specific point, this is the formula that you use. Not too bad, right? Okay.